All right, our final lecture in chemical kinetics is looking at how to write a rate law from the mechanism of a chemical reaction. Now, the last lecture at the very end, we talked about what a mechanism is. A mechanism shows us how a reaction goes from reactants to products. There are two types of mechanisms. There are elementary mechanisms, in which how the reaction is written is exactly how it occurs. And then there is multiple step mechanisms where the reaction occurs in a multiple set of collisions that leads to the overall product formation. Many times in a multiple step mechanism, intermediates are formed. These are substances that are neither are no longer present in the overall equation as either a reactant or product. They're formed and then they're later consumed. Same thing for catalysts. We're going to find out. A catalyst is consumed first and reproduced in a later step. It too is not part of the overall equation. So it's a multiple set of steps, and now we're going to learn how to write rate laws for each. Okay? Now, as I said before, if it's an elementary process, if it's an elementary reaction, how the reaction occurs exactly what the chemical reaction looks like. So up here I wrote a chemical equation of two nitrogen dioxides produces dinitrogen tetroxide. If you were to think about this conceptually, you would literally think of an NO2 molecule and another NO2 molecule crashing into each other. And again, with collision theory, two requirements have to be met. They have to collide with enough energy to overcome the activation energy barrier. In essence, we have to hit hard enough for the bonds to break, for new bonds to form. And secondly, it has to hit in the right spot. It has to hit in the right location so that products can form. Okay? If this is a successful collision, products are therefore formed. Now, we can immediately write the rate law of the chemical equation from it because the orders of the reactants are equal to the number of molecules involved in the collision. So if you are told that a chemical reaction is elementary, you can immediately write the rate law for it. So we write the word rate equals little k. The only reactant here is NO2, so we put it in brackets. Again, it's molar concentration. Brackets means molar concentration. And since two molecules are involved in the collision, the order of the reactant is 2. It matches the coefficients because how the reaction is written is exactly how it occurs. So we can write rate laws for elementary reactions just by knowing the balanced equation. Okay? And down here we see all the different possible scenarios that you can have. Termolecular means there are 3 molecules involved in the collision. Bimolecular is 2 and unimolecular is 1. These are the only types of rate laws we can get from those types of reactions because you can see the type of collision that is required in order to be unimolecular, bimolecular, or termolecular. Again, the only one that isn't on here is zeroth order. In a zeroth order reaction, the rate law is just simply rate equals K. If it's zeroth order overall, none of the reactants, their concentrations affects the rate of the reaction, and therefore they're not part of the rate law. All right, if it's a multiple step mechanism, now we end up having a series of steps. Here's an example utilizing tolls, in which the rate of the reaction is synonymous with the flow of traffic. And what we find out is that in a rate law of a multiple step mechanism is that the overall or output flow, the output of the chemical equation, the formation of final products, is really dictated by the slowest step of all the mechanisms. And you can see here in the first example, the slowest toll is the first toll, toll A. And the output of the flow rate out of the first step, those cars can quickly pass through B. They're not packed up or backed up as toll A is, and therefore toll A would be called the rate determining step. The step that dictates the rate of the reaction of a multiple step mechanism is called the rate determining step. Okay, the rate determining step is the slowest step of a multiple step mechanism, and the rate of that slow step is equal to the overall formation of products. And it doesn't matter where it happens. In the second toll example, you can see that toll B is the slow step, and therefore it dictates the flow rate of the overall formation of products, or the output flow of traffic, and it is would be called the rate determining step. So it doesn't matter if it's the first step or the last step. Wherever the rate determining step is, the slowest step, it will be or be found to be the step that overall dictates the overall kinetics of the chemical equation. On a potential energy diagram, as we saw in the last example, if here are my reactants, here are my products, step 1, here's the first collisional step, and step 2 is here. If this is a potential energy diagram, the first step has a lower energy of activation requirement. It takes less energy to get over the hump than it does to do the second hump. And therefore, in this example, the highest hump of all of them would be called the rate determining step. This would be the slow step of the mechanism. The second step in this mechanism would be the rate determining step because it has the greatest activation energy, and therefore there would be less potential collisions that could meet that activation energy to break the bonds to form new bonds. Okay? So when you see multiple step mechanisms, what you'll start seeing is multiple steps identified along with the overall equation. And over here on the very far right, they will tell you slow or fast. Okay? So it says here step 1 is the slow step. So the only step I have to look at for the chemical kinetics would be this top step. The rate law of this step should be equal to the rate law of the overall equation because the slow step dictates the overall flow of product formation. So, in a multiple step mechanism, each step is an elementary process. Just that there's multiple elementary steps, collisions that occur before the final overall equation is found. So, because we know each step in a multiple step mechanism is an elementary process, I can immediately write the rate law from it. So here I can write the rate law for the slow step. So I write the word rate equals K. Now if I look at step 1, they are both the same reactants, NO2. So I'm going to put NO2 in brackets, the molar concentration of it, and since there's 2 molecules of it involved in the collision step, it would have a rate order of 2. 2 molecules are needed. This is the rate law of the slow step, or the rate determining step, and it's also the rate law of the overall equation. Again, the rate law of the slowest step is the rate law for the overall equation. And if I look here, the question was, is the proposed mechanism consistent with the observed behavior? It says the observed rate law from the chemical evidence is rate equals K, concentration of NO2 squared. The mechanism matches. The mechanism matches. Secondly, the overall equation is given because we end up canceling out NO3 and NO3, and NO2 cancels, and I'm left with NO2CO plus NO plus CO2. Another common question they ask on the national exam is if I get this rate law for the overall equation is rate equals K, concentration NO2 squared, a question they might ask is the overall equation an elementary process? Well, the rate law of the overall equation would be NO2 to the first and CO to the first. Well, the rate law of the experimental evidence does not match the rate law of the overall equation. If the coefficients do not match the orders of the overall observed rate law, then we know that the overall equation cannot occur in a single event. It has to occur in multiple collisions, and one of those collisions is the slow step that dictates the rate of the chemical equation. So let me say that again. If the orders of the rate law do not match the coefficients of the balanced equation, or do not involve all of the reactants of the overall equation, then that tells you that the equation cannot be an elementary process. It does not occur in a single event. It occurs in multiple step collisions. All right, so go ahead, pause the lecture now, and let's do the problem at the bottom of page 1, please. All right, so the overall equation, I would just simply add up the 2 steps together. The O cancels because it's a product in the first step and it's a reactant in the second step, and therefore because it cancels out of the equation, it is an intermediate. So in CO, the single atom of oxygen is an intermediate. The overall equation would be 2N2O, two of them, produces 2N2 and an O2. Again, if they're on the same side, we simply summate the substances. And the rate law of the overall equation would be the rate law of the slow step. And in the slow step, we just have one molecule of N2O. So the rate law would be rate equals little k concentration of N2O to the first. So those are types of questions you might see in the national exam. Let's turn the page. All right, so what happens when the first step is not the slow step? Whenever the first step is the slow step, this again is an easy problem because the rate law of the equation will be equal to the rate law of the overall equation. Okay, so if we look at this first example here, the first step again is the slow step, so this is a very easy step in order to do the rate law for the problem. So I would write this as rate law, rate equals K, concentration of NO2 squared, because again there are two molecules of NO2 involved in the slow step collision, and right there is the rate law for the overall mechanism. Now, the second example, we see the slow step occurs in the second step. So again, the rate law of the slow step should be the rate law of the overall equation. Well, if I write the rate law for the slow step, I get rate equals K, NOCl2 to the first, NO to the first. This would be the rate law for the rate determining step. Okay. However, this cannot be the rate law of the overall equation, and the issue will be is the overall equation, the reactants are NO and Cl2. You will notice that NOCl2 is not involved in the overall equation. It's not a reactant, it's not even a product. What it is NOCl2 is an intermediate. And you can see up here in the steps for writing rate laws of chemical equations that an intermediate cannot be part of the overall rate law because it is not a reactant of the overall equation. So now what do we have to do? We have to do now, which means we have to substitute out the intermediate. So how do we do that? Well, the intermediate is formed in step 1. Okay, so if I look at step 1 here, you'll notice a key thing in all these problems is step 1 is going to have an equilibrium arrow. What that means is the rate of the forward reaction is equal to the rate of the reverse reaction. So if I were to write the rate law of the forward reaction, I'm going to write rate of F. For step 1, I would get K times concentration of NO to the first, Cl2 to the first. The rate law of the reverse reaction, so now this is an example, an introduction to what we call an equilibrium reaction, where the reaction goes forward and backwards. Okay? And now the reverse reaction occurs at the same rate that the forward reaction goes at. So now we get K times NOCl2 to the first. So now I'm looking at the reaction going backwards, so now the products are really the reactants in the reverse reaction. Now, what we tend to do here is because there's so many K's to differentiate them, and they all are different, is I'm going to put up here, since this was the second step, that would be K2, K1, and this one is called K negative 1. Negative 1 indicates that it's the reverse of step 1. Okay, so these are connotations we typically use in kinetics. We label each of the little k's based on what step they come from. Now, since the forward rate and the reverse rate are equal, I can now set these two equal to each other. So what I get now is K1, concentration of NO to the first, Cl2 to the first, equals K negative 1, NOCl2 to the first. Now, why am I doing this? Because what I'm trying to do is to create a mathematical equation that I can substitute out the NOCl2. All right? So now you'll notice to solve for the NOCl2 to the first, which we now have in this equation, I just need to simply get rid of this K to the negative 1. So I divide it out and move it over to the other side. So now NoCl2 to the first is equal to this entire thing. So now I can go ahead and substitute it into the rate law. So now the rate law has got K2, and now I replace the NoCl2 with this whole entire thing. So K1, K negative 1, NO to the first, and Cl2 to the first. And then don't forget there's another NO to the first. Right here now is the overall rate law where we have substituted out the intermediate. And this is the process you'll do every single time. Now this is probably the most difficult thing in this whole entire unit, and it's something for those of you that are struggling in the class that I could care the least about. This might be one problem in the national exam, and I hope you understand the other stuff much more so than this. But for those of you that are really trying to get every single concept and to maximize and try to get a 4 or 5 in the national exam, this is something that I would want you to try to practice a few times just to get used to it. But again, once you get the technique down, it's pretty simple. You write the rate law for the second slow step. You get rid of the intermediate by setting the forward rate and the reverse rate of step 1 equal to each other. We isolate the equation just for the intermediate, and then we do a substitution. Now to clean this reaction up a little bit, what we do is we say that the rate constant, the overall rate constant K, we say that K is equal to all of these other K's multiplied and divided. So now the rate law would equal or be rate equals K, where now the rate law is all of those values, K2 times K1 over K negative 1. Since there are two NOs, there's one here and one there, it's like having X and X, so it becomes X squared or NO squared, and Cl2 to the first. And right here ends up being the rate law for the overall equation, in which we have now substituted out the intermediate. Okay, let's turn this. All right, so now pause the lecture here. Here again we have the slow step being step 2. I would like you to write the rate law for step 2, and if it does include an intermediate, I would like you now to go ahead and do the substitution out. And let's see if you can get this one right. Okay, so go ahead and give it a practice. All right, this is an odd one in the fact that in the overall equation you end up getting a product. And that's because when we do the substitution down here, in the forward step 1 and reverse step 1, we end up having O2 is present in the reverse reaction of step 1. And therefore you can see the flow rate. It's the same exact process. Now again, on the national exam, I would never expect that you would see a product. Now again, what you need to know is these are not always absolutes. So it is possible to have a product, but again, for this national exam, I would never expect, I've never seen them do this to you. But here's a harder problem to show that just the possibilities of what you'll see potentially in college and beyond. But the process is what I want you to see. So again, you write the rate law for step 2. The intermediate is O. So now the step 1, again, you'll notice that it's an equilibrium arrow. So the forward rate of step 1 is equal to the reverse rate. The rate forward is equal to K1 times ozone to the first, and the reverse reaction is K negative 1, oxygen to the first, O to the first. We set the two equal to each other, and then we divide out everything except the intermediate. In this case, the oxygen atom is equal to K1 over K negative 1, ozone, and then oxygen on the bottom. And we do the substitution, and then we do the cleanup. So it's the same steps over and over again. There are problems like this in the back of your textbook. Continue to do that if you want the additional practice, but those are the steps. And it's just like riding a bike. Once you learn how to do it, just repeat it over and over again. Okay? But for the most part, just expect most often to see this first step be slow. And if you can do that much, for the most part, you know 95% of the material on this exam. Okay? All right, a couple other things I just want to review real quickly to finish off this lecture in this unit. We talked about these in the last one, but they're so important I want to review them one more time. Here again is a potential energy diagram, and the red line is the uncatalyzed reaction. If we add a catalyst, first of all, a lot of times they'll ask you in the national exam to sketch what would happen if a catalyst was added. You must start the catalyzed reaction in the same exact spot as the uncatalyzed reaction. The the overall reaction will stay the same, even if a catalyst is added. Therefore, the reactants and products of the overall equation will stay the same. And therefore, the start and the end of the potential energy diagram will be the same. The difference will be the height of the activation energy. Again, the activation energy is from the reactant or the end of the last step to the next step. It's going up to the peak of the hump. This is the activation energy. Okay? So what a catalyst does is it causes a different pathway. We can see here that in the red uncatalyzed reaction, it is a one-step. It is an elementary process. In the catalyzed reaction, it is a two-step mechanism. And the second step is the slow step, but the overall activation energy is still lower than the activation energy of the one-step mechanism. So what a catalyst does is between the reactants and products, it lowers the activation energy, and therefore, because it lowers the activation energy, it causes the reaction to be faster. So if you are asked to draw a catalyzed reaction on the national exam, and because it's a different mechanism, usually it will be a different number of steps because it's a different mechanism to get to the products. But the key thing is it starts and stops in the same spot. It's still the same overall equation. The difference will be it lowers the activation energy, and it might change the number of humps. But just make sure that the tallest hump in your catalyzed reaction is still lower than the uncatalyzed reaction. One other note about a catalyst does not increase the amount of product formation. We don't get more product. The amount of product formed is dictated by the amount of reactant that is given in the overall equation. What it does is it lowers the activation energy, allowing for the rate to be faster. We get the product formation faster, but we just don't get any more product formation. Okay, that's a key step in the mechanism. Okay? All right, one other thing with a catalyst, I want to briefly mention this last page. Okay? Oops. My bad. Let's say this was the overall mechanism for an overall equation. Here, if you were to add up the overall equation, the C would cancel out of here, and we'd get 2A plus D produces 2B. This is the overall equation. But you're going to notice that C is not part of the overall equation, but it is involved in the steps. In this case, however, C is not an intermediate. It's not an intermediate because it is a reactant first, and it's a product second. To be an intermediate, it has to be formed. It has to be a product first and a reactant second. What is C now in this overall mechanism? C is not a catalyst. Actually, C is a catalyst. And that's what a catalyst does. A catalyst causes the reaction to go a different pathway to get to the overall equation. But it usually causes the mechanism to be more steps, but it lowers the activation energy of the equation, causing it to go faster. So a catalyst in a mechanism will be a reactant first because we add the catalyst with the reactant to cause it to go faster. So it's a reactant first, and then it's produced later on, and therefore it does cancel the overall equation. So now you have seen a mechanisms how it includes an intermediate and how it can also include a catalyst. And sometimes it can include both. Sometimes a mechanism might have a catalyst and an intermediate, and you might be asked to identify who is who. So again, it's the order in which they are reactants and products in the mechanism. All right, the last thing I want to talk about again is Maxwell-Boltzmann. In Maxwell-Boltzmann, if you increase the temperature of a reaction, you see the shift. This is the colder reaction. This is the hotter reaction. A lot of times you'll see a little dashed line, which is the activation energy barrier. Only the molecules that are to the right of that line have enough energy that it can break bonds in order for products to form. It goes over the hump, and therefore products can be formed. Adding a catalyst does not change the shape of Maxwell-Boltzmann. What adding a catalyst does is the activation barrier is here. Let's say it's 100 kilojoules, but by causing a new mechanism, the catalyst caused the activation requirement to maybe go down to 75 kilojoules. The shape of the graph has not changed. The only thing that changes the shape of Maxwell-Boltzmann is temperature. Adding a catalyst just tells me what point on this graph, what x value, gives me a collision that meets or exceeds the activation energy. In both cases, 1 and 2, we see that the shaded region, there are more particles in the shaded region. And this is a critical thing right here. Again, this is the most important verbiage that I have for this entire unit. And I want you to please get this down, not only in your notes, but also for the national exam. If you increase the temperature, the rate of the reaction increases. The rate of the reaction gets faster. If you add a catalyst, the rate of the reaction gets faster. On the national exam, I can guarantee you somewhere in the national exam they're going to ask this question. Why? Explain why the rate is faster. And what I boxed in is what you want to state. When I add a catalyst, it lowers the activation energy requirement, and therefore there are more collisions that meet or exceed the activation energy required for a successful reaction to occur. If there are more successful reactions, the rate of the reaction is faster. If I increase the temperature, why does the rate of the reaction increase? At an increased temperature, the molecules move faster. Therefore, there are more collisions that meet or exceed the activation energy required for a successful reaction, and therefore, since there's more successful reactions going on, the rate of the reaction is increased. So, the increased temperature causes more harder collisions. Adding a catalyst lowers the activation energy requirement. But the key thing is right here. Explicitly, you want to state in your explanation that the number of collisions that meet or exceed, that are at the activation energy or greater, will overcome the activation energy barrier for a successful collision. Make sure you state that exactly for verbatim, and if you do that, you're guaranteed to get that point on the national exam. Okay? All right, now you've reached the end of the unit. There will be a quiz in the middle of this week on mechanisms and potential energy diagrams. And then I will have a review out early this week for you to start working on it in preparation for next week's exam. And that wraps up semester 1. Again, thanks for listening.